Another one. Okay, so integral over width is the average value. So you want to make sure you show the setup. So labeling your integrals is a good idea too. Average value equals, and we're going from 0 to pi halves. So the integral from 0 to pi halves, because it's not a calculator problem, instead of just putting f of x, I actually wrote the expression for the function there, dx, over the width, which is pi halves minus 0. So this step right here is important because it indicates your method, it's your setup. Now, when you simplify, you're really dividing by pi halves, which is the same as multiplying by 2 over pi, so you can kind of simplify it down to there. Now, you need to figure out what the antiderivative of that is, which is going to require integration by parts. And is this one where we can use the tabular method? Yep. X squared, or x cubed, sorry, is what we're going to call u, and cosine is one of those repeaters, so you can let it be dv. So in the left column, just run x cubed all the way up to 0 with the derivative. And as you take the antiderivative of cosine, a couple things to keep in mind. You're going to have a correction of a 1/2 every time. And you need to be very mindful of the negatives, because a problem like this, you can be off just by one little negative and can ruin everything. So make sure when you find the antiderivative, before you go to the next one, just check. Check to see if the derivative is in fact what you're getting. So like down here, negative 1/4 cosine of 2x, its derivative is negative sine, which times that negative makes it positive. So you make sure you're getting the right plus or minuses. So that's the column right there in the middle. And then plus minus, plus minus, plus minus. Okay, so the diagonals, here we go. We're going to get a 1/3 x cubed, or 1/2 x cubed sine of 2x, which I wrote right here, with the 2 over pi out front with brackets. Pick up the next sign, it's minus, but then notice your next product is going to be times a negative. So it turns it to a plus sign. And you have a 3/4 x squared cosine of 2x. Pick up the next sign, plus, but the next product is negative, so it becomes negative now. 6/8 is 3/4 x to the sine of 2x. Pick up the next sign, which is minus, and then it becomes 6/16, which is 3/8 cosine of 2x. And of course, the next diagonal is 0, so you could stop, but because it's not a definite integral, you put the evaluation bar from 0 to pi halves. And notice that 2 over pi is still way out in front with brackets. We're taking them along for the ride. So our terms ended up being plus, plus, minus, minus. Now, when you plug in, it seems like a daunting task. You got 2 over pi out there. When you plug in your pi halves to the two terms that have sine of 2x, it becomes sine of pi, which becomes 0. So the first and third term go away, and the other two terms, cosine of pi, end up being negative 1. So that's the first one there in the brackets. And then minus, when you plug in the bottom, don't just take for granted that everything becomes 0, because it's not. Any term with a sign or an x in it goes to 0. But notice the very last term, minus 3/8 cosine of 2x, does not have a 0 in it, nor does it have an x. So you do end up with a minus 3/8 there. And if you clean up all of that, you're left with a negative 1 times 3 pi squared. So it's a negative 3 pi squared over 16. And then you're going to have a minus, wait, is that a minus 3/8 times a negative? Sorry, it becomes a plus 3/8 right there. And then minus from the plugging in the bottom, minus another negative 3/8, which makes it a plus 3/8. So you can combine those and get 3/4. I put it in the front, and that's as far as I went. 2 over pi times the quantity 3/4 minus 3 pi squared 16. Not a very pretty number. I guess you could get a common denominator there and multiply through. But from there, I went to the calculator, because it just didn't seem right. It seemed like it was too ugly, right? So I typed it in to the calculator right here, and I did it in 2 steps. I did 3/4 minus 3 pi 16, and then divided by pi and multiplied by 2. I got negative 0.70063. And then I went down here and typed in the integral in radian mode over the width, and I got the same answer. So this answer here and this answer here are the same. So as ugly as it was the right answer. So a good way to review average value in a new context. Average value is always integral over the width. All right, example 13. That's the last one of the section here. Let's finish strong. We have e to the x divided by secant of x. We have a quotient now. Any idea how to do that one? What's that? Integration by parts. Good idea. Good idea. What do I call you? E to the x? What do I call dv? 1 over secant? Cosine. Oh, I like that. If I call it cosine of x, that gets rid of the quotient and puts it in terms of cosine, which makes me a little happier. Now you have two factors there, and neither one of them is the derivative of each other, but both of them are repeaters, right? I know how to differentiate and exponentiate both of them. Is this the first time we've seen that? One of them's been x, where it's always kind of expired. This is the first time we've seen a product of two repeaters. U dv plus or minus. Which one do you want to call u? E to the x? That's going to be a real easy derivative, right? If you take the antiderivative of cosine, you're going to have to be a little bit more careful with your pluses and minuses, right? People tend to mess those up a little bit sometimes. So if it were me, personally, I would actually choose cosine to be u, just because I'm more comfortable taking the derivative of cosine than I am the antiderivative. Because I have it down pat that if it's a derivative and it starts with co, it's going to be negative. But sometimes going backwards, I goof up. And sometimes I don't check. And I know that e to the x is going to be a super easy antiderivative. So it doesn't really matter which one you do. All right, so here we go. Cosine. The derivative is negative sine. The derivative is negative cosine. The derivative is positive sine. The derivative is cosine. And I could keep going forever and ever. I already repeated it now, so wow me. And then this one, e to the x. The antiderivative, e to the x. It's antiderivative. E to the x. It's antiderivative. E to the x. It's antiderivative. E to the x. If you're watching this at home, it didn't get stuck in a video loop. It's actually, we're taking antiderivatives. E to the x. E to the x. E to the x. All right, fun. Plus. Oh, no, we don't want to get caught in that loop. Plus, minus. There's a loop. Plus, minus. So on and so forth. We continue all of them. When do we stop? I don't know. Well, let's see. I told you that if neither one repeat, you're always going to take the first diagonal product. Okay? So let's come back up here and say that this equals e to the x times cosine of x. And then minus. Pick up the sign of the next term. And then you look to see if you can integrate the horizontal product, right? Can I integrate e to the x sine of x? Nope, that's going to require another integration by parts. So we'll go ahead and take another diagonal product. It'll be e to the x times negative sine, which makes it positive e to the x sine of x. Come across, pick up the next sign, it's positive. We look to see if we can integrate the next one. Can we integrate negative cosine e to the x? No. But what do you notice about cosine e to the x? We can't integrate it, but it is the same one that we started with. So if I don't tie it off sometime, I'm going to be doing this diagonal product forever or until I expire, right? So let's go ahead and tie it off with an integral, and I got a negative e to the x cosine of x dx. So this is why you want to stop here. When you get to the repeated one that you started with, beyond the first one, you're always going to take the first diagonal product. But the next time you get to the one that you started with, go ahead and tie it off horizontally. And here's why. You have now created an integral equation. Let me get this out of the way. V, you didn't come with it? Why not? All right. Here's what you could do. We're trying to figure out what e to the x cosine of x dx is. I actually have a negative term over here that has a like term to the one on the left. So look what I could do. I can add that term to both sides. Yeah, back in Algebra 1, right? We did that. Ooh, Algebra 1. In calculus? Really? Yep. We'll do it the way we did it in Algebra. What happens to the term on the right side? It cancels. And what happens on the left side? I get two of them. So I get 2 to the integral of e to the x cosine of x dx equals e to the x cosine of x plus e to the x sine of x. And I better put my plus c there now because I got rid of the integral. And I know it's supposed to be there. Dang it. How does that help me? What is it that I'm after? I'm after this, right? That's what I want to know the answer to. That's right here. I'm currently multiplying it by 2. How do I do multiplication by 2? Divide both sides by 2, or multiply both sides by a half. So I get that, which is what I wanted, equals 1/2 of this quantity. And of course, you could distribute to the 1/2 and let it absorb the C can absorb the 1/2, so you can put it outside if you want. And guess what? We're done. This is a pretty typical strategy when you have 2 repeating factors, e, cosine, and sine. You're going to do the tabular method and tie it off when you get to the product that has the same factors that you started with. Then you'll collect like terms on one side, double, triple, whatever, and then solve for the integral that you wanted. That's it. Will you see one like that on the AP exam? Who knows? Maybe not. Will you see one like that on my exam? Yeah, I like those. Those are kind of fun. Once the horizontal product, past the first diagonal, okay? Once the horizontal product becomes the same as what we started with right here. Okay? Does that make sense? Yeah. Okay, and so we had that right there. How do we know that this is right, besides the fact that we did it together and we know we're awesome collectively? Let's take the derivative. You want to do that? Now, if we're going to take the derivative, we might want to simplify, right? So what can we do there to prevent ourselves from having to do 2 product rules? What's that? Pull out an e, right? So I have a 1/2 e to the x, beefy bracket, cosine x plus sine of x. Yeah, that works great. Plus c. Can I call cosine x plus sine of x 1? Boy, that'd be great if I can call that 1. Is that 1? No. Why not? They're not squared. Can I square them and call them 1? I could, but it wouldn't make it right. Okay, let's take the derivative. Let's see what we get. If we take the derivative of that, we get e to the x cosine of x, which is what we were expecting. Is that any way to check? No, that's just forcing it to be what you're trying to determine it is. So yeah, you need to show more steps than that, right? Like on a free response when I say show that the derivative equals that and your second line is the answer, right? You're kind of missing the guts of the problem. Schroeder. Have you tried that? All right, let's try it using the product rule. What's the derivative of 1/2 e to the x? 1? The derivative, we're doing the product rule, so the derivative of the first factor goes first. The derivative of 1/2 e to the x is 1/2 e to the x. Good. Times the second one goes along for the ride. Got that down. And then plus 1/2 e to the x times the derivative of the second. What's the derivative of the second? Negative sign, good. Plus cosine. And then finally the derivative of plus c? 0. Should we just write the answer now below that, or should we actually expand? You could expand, right? You could distribute, or notice again, I want to get you in the habit of looking for common factors first. We still have 2 terms there, right? And it's partially factored. So rather than distribute the 1/2 e to the x, what could we do? Pull out the 1/2 e to the x. Yeah. That's simplifying early and often, making things small before you make them big. And we're left with cosine of x plus sine of x. And then what? Minus sine of x plus cosine of x. Yeah. And now we can combine like terms on the inside. What happens with the signs? They cancel. And I'm left with cosine plus cosine, which is 2 cosine. Yeah? And round and third heading home, right? What's happening now? 1/2 and 2 divide out, giving e to the x cosine of x. And just to put it in the final or the original format, multiplying by cosine is the same as dividing by what? Secant. And is that what we started with way back over here? Yes, it is. Nice. So it works, right? So this is the fun one where you have double repeaters and you have to terminate the tabular method by tying it off horizontally with an integral once you hit the original product that you started with. Okay? That's it. Tabular method works every time. If not, use the Z method, the Zorro method. If only Poncho were here, we could help him, huh? Yeah. All right, integration by parts, 5.4, worksheets due tomorrow. Y'all have any questions on it? Is it a good one? Have y'all started it? Draft 2? Maybe finished the rough draft? Short answer. Oh, yeah. Maybe you could add a page below it on notability? True, yeah. I thought I left enough space for y'all, but sometimes that doesn't happen. Have you run into a roadblock anywhere on here? If not, we'll just go right into the next section. No, that one looks good. That one looks good. Pretty straightforward. That one's pretty straightforward. Ooh, a slope field in there. A slope field with integration by parts? Yes, please. There it is. These are the ones that get cramped, you say? Yeah. Yeah. Especially like letter B. Letter B. If you draw the table, oh, yeah, yeah. You could do the table and then shrink it down, right? Mm-hmm. Those all look pretty straightforward. You think you're going to get a hint like that on the AP exam? Does a hint like that help? Did it help you here? No? It didn't help? That's a pretty good hint, right? R cubed is equal to R squared times R. How is that a hint? Has anyone done that one? You get it now? You see it? Yeah, it's a subtle hint, but it's all really I can give you without giving it away. If you looked at pattern recognition, like if you saw this problem just in the grand scheme of things and it wasn't necessarily on the integration by parts worksheet, right? You would look at the inside function and you'd be like, the derivative of R squared is 2R. We are off by an R squared. So maybe use substitution if you're off by an R. But use substitution really only works when your inside function is what? Linear. Is 4 plus R squared linear? Nope. So that's out the window. So the next thing, since you're seeing a quotient, is maybe you think inverse trig. Does it fit any inverse trig pattern? Well, the problem is they're both positive. So if I factor the negative out of both of them, it's going to change both the signs. And one of them is going to be I, and that doesn't work. Right. So it doesn't work for two reasons. You get an imaginary root, and remember, for arc sine, one has to be positive, one has to be negative. The signs have to be opposite. They're both positive. The only one that works when they're both positive is arc what? Tangent. But arc tangent's also the only one without a square root. So is there an inverse trig? Nope, not inverse trig. So what to do? What to do? Integration by parts. Very good, Mr. Miller. What do we do with R cubed, though? I've read that same article. It's a fascinating 3-sentence article. Uh-huh. Is that how you would split it up, or would you put the r squared in the numerator? Well, let's see. By writing it as a product of two things, do I know how to take the derivative and the integral of r squared? Yes, so that one's free to float as u or dv. But on the second one here, by writing it as r on the top and not r squared, I only know, well, I guess I do know how to take its derivative, but I also know now how to take it.
Please pardon the interruption, teachers. Coach Bronner is selling playoff t-shirts and six-man t-shirts.
Antiderivative. I know how to take its antiderivative. So, if you know how to take the antiderivative and the other one's the power function, which one do you want to let equal u? Which one do you want to let equal u? R squared. And the other one's going to be r times 4 plus r squared to the negative 1/2. I'll bring it to the top. Negative 1/2. Plus or minus. Oops, plus. Sorry. So let's go. I got 2r, and then I got 2, and then I got 0. The antiderivative of this, by the power rule, I'm off by a what? I'm off by a 2, so I have a correction of a 1/2. And then I get the power rule, 4 plus r squared to the negative 1/2 plus 1 is 1/2. And then instead of dividing by 1/2, I'll multiply by 2. So notice that ends up just being the square root of 4 plus r squared with a minus. Now, as I start taking the antiderivative, I know I'm going to take that first product. So it's going to be r squared times the square root of 4 plus r squared. I go and pick up the sign minus. The question is, before I go on the diagonal and take another derivative, can I integrate the horizontal product? With this 2 and the 1/2 gone, can I integrate 2r times 4 plus r squared? I can, because this is now my inside function, and its derivative is 2r exactly, so I'm not off by anything. So I'll tie it off with a 2r and a 4 plus r squared to the 1/2. So there's how you do it. And then you can integrate that one by another pattern recognition, and then you can evaluate it. So now you can finish that one. That is one that's beyond the pale or beyond the scope of AP exam. You don't have one like that. That one's a little tricky, especially without the hint. Okay, I thought I would start the next section, but since it's already 10 minutes in, I won't. I guess I'll give you all the rest of the time to work on the worksheet. I'll turn the announcements on. Sound good? Okay. All right, so tomorrow we'll start partial fraction decomposition by the Oliver Heaviside cover-up method.